Okay, so this time I'm going to have a go at add with carry. And if you didn't watch the last video, then none of this, what we're going to do here, is going to make any sense at all. The first thing I need to do is create a new unit test file to stick the add with carry tests in. Okay, so first thing I want to do is probably just going to attempt one of the add with carries, the absolute, because I think that's probably quite an easy one to do. Absolute addressing is quite simple. So I'll just try and write a really basic test for that to start with. So we'll start by just trying to add 0 and 0 together, because that's easy. I'll also put a 0 in the carry flag. So we're going to have 0 in the carry flag. Just don't need that hex for the 0 really, do I? Oh, I need carry flag false. Is that right? Is it going to let me do that? Flag. There we go. So I want nothing in the carry flag. I want nothing in the A register. And I want the add with carry ADC Absolute. And then for the absolute, we just have a 16-bit little endian address that lives in the 2 bytes after there. So I like to just stick that in 8000. So, and then at address 8000 will live the value that we want to add. And we'll make sure that there's a 0 in there as well. So this is just the let's add 0 and 0. ADC can add 0 to 0 and get 0. That's a weird test. Well, that's what we're going to call it. It expects 4 cycles. And what do we expect afterwards? We expect the A register to have 0 in it. We expect the carry flag to have, we expect the carry flag to be false. In fact, I'm going to do it as an expect equal, and I'll tell you why in a minute. So I'm expecting the carry flag to be false. I'm expecting the 0 flag to be true. And I'm expecting the negative flag to be false. Is there anything else that can be affected by this? Overflow flag, there we go. And it doesn't overflow. Set if the sign bit is incorrect. So it doesn't overflow, so it's set to false. And then we've got these, we have actually got a leftover function here for expect unaffected registers. So anything else that's unaffected can live in here. So interrupt, decimal, break. It's just interrupt, decimal, and break are the flags that don't get affected, and we'll just put that in a function so we can keep calling that every time. So I think that's a good starting test to get our very first simplest thing we can do with add with carry, which is let's add 0 to 0. It's a pretty lo-fi place to start, but that's where we're going to start. Arithmetic, add carry absolutes 60. Okay, does that compile? Totally does. We expect one failing test with the instruction not handled. So let's go straight in. Let's jump straight in and try and just get that one working. So we've only got one test, but we are going to try and just build this up as we go. ADC Absolute. So the first thing we need to do is get the address, and we have a function to do that, address absolute. So that's the address where we're going to read the byte from, and then we can read the byte. What does that byte give us? That gives us the, I'm just going to call that value. What's the right term? What's the right term for? Is the right term operand? In mathematics, operand is the object of a mathematical operation, the object or quantity that is operated on. I suppose it's operand. Let's call it operand. What the hell? we've read the value from memory, we've got the operand, we can add that to the A register. That may or may not pass. Let's see. I don't think that'll pass. It's not enough to make it pass. Because the negative flag, yeah, we're just setting up the negative and 0 to be the opposite of what we want. We'll set 0 to be false. Can we get that to fail a bit more? We just want as much failure as we can. There we go. And we want the overflow flag to be true. So just setting those to the opposite, just to get more failures out of this. There we go. So we've got 3 failures out of that because we didn't handle that situation. So I'm going to do something a bit weird, and that is I'm actually just going to set these values to what I think they should be to make this test pass. So the 0 flag is true. The negative flag is going to be false, and the carry flag is going to be false. And do we need any others? Overflow. The overflow didn't overflow, so it's false. So let's see what we get. And we pass. So you can see that this is a bit crazy because what I've done here is I knew what the test did and I wrote the code that made the test pass. Now weirdly, that is what you're supposed to do if you're doing like test-driven development like this. You just write the code that makes the test pass. And what it also then shows you is that, well, you can't really do just one test, because this one test on its own isn't enough to test the program works properly, because there's more than one outcome from ADC. So what I want to do now is put in more tests and build up more failures and then keep fixing them, but making sure that this test still passes. So what I don't want to do though is rewrite this code a billion times. So what I think I'm going to do is something we've done before, but I'm going to extract this out into a function. So let's just call it that. I'm going to paste all that in there, and then I'm just going to call it from in here, like that. Does that still compile and still fail? That's what we want to know. Yeah, still pass in this case actually. Yes, it does. Now what I want to do is parameterize this so that we can pass in all the parameters that we need to make a... I'm going to want to test add with carry absolute loads of times. I'm going to want to do the same thing with absolute x and so on and so forth. What I think I want to do is make a little structure with the test data. Let's call it that. ADC test data. And I'm going to pass in all the stuff that I want to, like all the prerequisites and what I expect afterwards. And then I can run this test loads of times on this data. And the reason I'm doing it as a struct instead of just passing the parameters in here is because I want these like parameters to be kind of named, and you don't really have named parameters in C++, where you can say this value equals this one and you pass it in so you can see what it is. Otherwise I could end up with a thing where I'm just passing in loads of stuff like that, and that's not what I want. I want to be able to see what it is I'm doing. It'll just become clearer if I write it. So what I want is we want a byte. So we want the value that we want to put in the A register that we're going to add with. We want the, let's call this operand. Yep, so we want the A register, we want the operand. We're always doing add, so we don't need the operator, we just need the thing we want to operate on. We need the carry as well, don't we? So that's a bool. So we want the carry before. Okay. So this is the add with carry. We want the carry, the A register, and the operand, and that's what we need to put in. Now, what do we expect out at the other end? So we want the answer. So what do we expect if we take the carry? Let's just say that, call that one carry. The carry, the A, and the operand. What is the answer to that sum? So that's the expected answer. And then afterwards, we want to know expect carry What do we want out? What else do we want? Expect 0. I'll just call that C. Expect C, expect 0, expect negative, and expect overflow. So that's our little bit of data that we need. So what I want to do then is pass in one of these. That's been unreferenced. So let's just take that out for now. I just want to get this to just make sure this compiles before I move on. Okay. So in effect, this doesn't, unreferenced variable, what's that? Uninitialized local variable test was used. Oh, I really didn't initialize it. How does it know that? Is it because what happens if it's got an initializer like that? Isn't that fine? Oh, it is. Oh, well. Still, that's fine. I mean, it's an actual error that we want. That is not initialized, but I think that's the only error we've got left now. So I'm going to put these back in. And then what I want to do, and this is the reason I did it like this, is because I want to be able to just set these values up like the way we had it. So this was what we were doing before. This was testing the A with the operand, testing 0 with 0. The carry is set to false. So that's my sum that I want to do. And then I expect the carry to be false. I expect the negative to be false. I expect the overflow to be false. And I expect the 0 flag to be true. So that's just setting up basically the same test that we've just done. And except now we need to use these values that we had in here. So this is the carry. This is the A register. This is the, so with the expect 0, I'll set it to the opposite of what it was. So we can set these to the opposite of what we want them to be at the end. Just to try and get the test better. Okay, and there's our operand that goes in there. And what else have we got? So at the end, we've got the test. We expect the answer, and then test, expect the carry flag there. Yeah, we expect that carry flag because we put in one carry and we can get out a different one. So that's actually fine. We expect that 0 flag. We expect negative. And we expect the overflow flag. Okay, so if all goes correctly, this hasn't changed anything. All we've done is we've refactored that code so that we've got a repeatable, rewritable test, and we don't have to rewrite all the stuff. We just pass in the parameters that we want. Except it doesn't work because I put 2 dots in there for some reason. Oh. Did I not give an answer? Whoops, didn't give an answer. I expect the answer to be 0. There we go. Carry is false, the A and the operand, and then that's what we expect in the answer. So that's the 0 plus 0 equals 0. There we go. So that is just a refactored test. That's really all I've done there. So now this just makes my life a bit easier now that I can actually now do this. They can add carry and 0 to 0 and get 1. I mean, that's really what's going to happen here. So we do the same test except we've got something in the carry flag. And that should just give me the answer 1 because the carry gets added on. Remember, this is add with carry. We can just run that exact same test. The difference here is we don't carry, it's not negative, It didn't overflow, but we don't expect 0 anymore. So, new test now. Right, there we go. So our first test still passes, but that one fails because the answer is incorrect because we didn't add the carry bit in. So let's see if we can fix that first. One of the things we've got to do is we've got to add the carry flag on. I mean, I can just do that, really. Does that work? Does that get rid of that one error? It does. So the only thing we've got now is the 0 flag is incorrect. So we should set the 0 flag based on whether the A register is 0. So does that make our second test pass and the first one? It does. There we go. So we've got two tests passing. I mean, that's not a full suite of tests yet, though. We need to do more because clearly these registers are just being fudged. So we definitely haven't done enough to make this work properly yet. Let's see if we can do something a bit harder than that. So let's do something that overflows. So ADC can add 1 to FF and it will cause a carry. Okay. So we won't set the carry flag to start with. We'll set the A register to FF. Set the operand to 1. Now, this is a weird one. What answer do we actually expect? And I don't really know about that. All I know is that we expect the carry to be true, and we don't know what to set for the rest of these. Let's see. If it wraps around, it probably wraps around to 0. I think that's right. So we actually expect the answer to be 0. Now, in this case, the 0 flag should be set, because the answer in there is actually 0. The overflow flag will not get set because the sign, although you could treat this, you can think about this as assigned a negative number plus a positive 1, depending on whether you're thinking about this as signed or unsigned. It doesn't matter in this case. I think this won't cause an overflow. I could be wrong about that. And 0 is not negative, so that's definitely got to be set to false. Have I got that right? Yeah, this should give you 0 with a carry. Yeah, it's not going to cause a signed overflow because, yeah, actually what would happen here is if this was a signed addition, FF, all the bits set is -1, and that would actually give you the answer of 0. Yeah, so 0 with a carry. So you have to remember that when the CPU is doing these additions, it doesn't actually care whether it's signed or not. It's you that actually cares. But it's telling you whether if you were doing a signed operation, it needs to tell you whether it was correct or not, and that's what we've got to do here. So I think that's a good test. So that should be another one that fails, and it does. What does it fail on? The carry. The carry didn't get set, and that makes sense because we don't think we're actually setting it, are we? No, we're not setting the carry. So we need to know when an operation would have caused an overflow. I'm not sure what the best way to do that is right now, actually. Maybe I could do this operation as a 16-bit. I mean, this is cheating because this isn't how the CPU would actually do it. But maybe I could do this sum as a 16-bit operation. So I could put the A register in there, and then I could sum the operand and sum the carry flag. And then I could set it back into the A register at the end and, you know, just clamp it, mask off so it's just the 8 bits, and I don't think that would matter, but I'm going to do it for completeness. If I did that shouldn't change. Let's just see if that doesn't change what we've got. We've still got one failed test. Ooh, is it still the same one? Yeah, it's the one that's causing the carry. But in theory now, I would say that we can actually find out if the carry flag needs to be set by reading that sum. We've got FF. We add 1 to it, we get 100. So yeah, so you can see there that because there's a 0, 1 in the high byte, that's going to give us our information that we've actually overflowed. I don't know if there's a better way to do this, because what we're really doing is we're doing an 8-bit addition, but we want to know that the 9th bit got set, so we really need more bits. So if I do this as a 16-bit addition, and then I can just work out this carry flag needs to be set. And we can do that kind of with the opposite of what's going on here. Whereas if I mask off just the high part of the sum, if that's greater than 0, then the carry flag gets set, I think. Let's try that. See if that gets us 3 passing tests. Oops. Oh, and it does. So that was probably the way to do that, to get the carry flag correct. So we still probably don't have enough, because clearly we're fudging these in, the negatives and the overflows. So let's try and get the negative working here. So let's do another test. And let's try and get something that produces a negative result. So ADC will set the negative when the result is negative. And that's really all we care about here. So we don't care about the carry. We'll just put 0 in the register, and we'll put in the operand, we'll put -1. Now we expect the answer to be -1. We expect the carry to be false. We expect the negative to be true. It didn't overflow. The sign bit didn't overflow, and it's not 0. I don't think this is going to compile though, and you'll see why. Because it's signed unsigned mismatch there. What I think I might do is I'm going to make a macro. Everybody loves macros. Let's make a macro. What the hell? I'm going to make a macro that takes this A value and it casts it to an M6502 S byte. Yeah, why not? Just to save me typing static cast everywhere. I don't know. I think this might be actually better. So I'm just turning. Oh, I need to. Sorry, it's. I need to turn it. I've done the opposite of what I want there. I need to turn it into a byte. So I'm just taking the. Oh, is that? Doesn't look like it's happy with that for some reason. Oh, because it's not happy with it. Okay. So I'm just taking the negative number and I'm turning it into a, I'm just making it so it can be used as an unsigned number. Because in effect, remember, the CPU doesn't care. It's always doing this as an unsigned addition. It doesn't actually care. What it cares about is whether the overflow flag is correct when it's doing signed additions. And this isn't going to cause an overflow. So in this case, it should work, but what it will do is it won't set the negative flag correctly because we haven't done that yet. So is that what's gone wrong? That's what we want it to go wrong. Yeah, negative flag. Expect negative flag. It's funny, it just scrolls off there. But anyway, the negative flag's wrong. So now we can fix that as well. So the negative flag's a pretty easy one, I think, because we can just and it with we've got a mask for the negative flag bit, and if that has been set, then it is negative. So that is all we need to make that bit pass, and it is. So there's definitely one more fudge going on here, and this fudge is that the overflow flag. So we have to set this when the sign bit has gone wrong. So this one's going to be a bit more tricky, but we need to engineer a situation where the sign bit will fail us. And we do that, remember, we can do that with either adding two positive values together that would go outside of a sign bit range, or we can do it with doing it with two negative values. So I'll do it with two negative values to start with. Add with carry, what will this one be? We'll set the overflow when I'll put when signed addition fails. How about that? So we can get that to happen by sticking negative. The biggest negative number we can have is minus 128, and all we need to do is add -1 to that. And here's the funny one: is what do you expect for the answer to that? And that's a good question. But we do. Oh, and what do we expect for the carry and the negative, and so on and so forth. So we've really got to work that out. So let me just see, what would it be? You can do it in here. So minus 128, it's got the minus number there. I think it's all zeros. How many is that? 1, 2, 3, 4, 5, 6, 7. Let me check that on the calculator. Stick this in byte mode. 1, 2. This is weird. It won't let you type 128 in the negative. You have to type the negative first and then the 128 because you can't have that value. Yeah, it is 1 with all the zeros. So that would be our A register. And the operand here is going to be -1. That's 1. I think that's all the bits set, isn't it? I think that's all the bits. I think it's 1 negative. Yeah, that's all the bits. So that clearly must cause a carry. What do we actually expect in the answer? You're going to get 1, 1, 1, 1, 1. You're going to get a 0 and all ones, and you're going to get a carry. So we definitely have a carry. It's not going to be negative. That's because this last bit here is going to be 0. Let's put the answer in there. It's going to be, you get a 0 in there, and these will all be 1s. So that's what's going to happen for that binary addition there, and it's going to have carry. Carry is going to be 1, and negative is going to be false, yeah, because it's this bit isn't set. Overflow, it has overflow because remember this meets the criteria of we've got a negative, and we added them together and we got a positive, and that's just not possible. So that has caused a signed overflow. And the 0, it can't be true because this is not, it's got 1s in it, so it can't be 0. So to answer our question is, what do we expect in there? Is that 127? Is that what we're going to get? I think we did this as one of the examples. Yeah, it's 127. So that's minus 128. That's -1. And that's 127. So that's what we're going to get. We're going to get 127 as the answer. We're going to get a carry. We're not going to be negative. We are going to get an overflow. And it's not going to be 0. So that's all good, I think. I don't know if there's any other edge cases for this, but that has got to fail. Yes, because the overflow is not being set correctly. So you can see here, that's the one we've not really handled yet. So how are we going to handle that? So as far as I'm aware, and I could be wrong on this, if we look at the negative bit on the operations at the start, if they are both the same, so that say both values are negative, and then the result at the end is positive, that must be an error. And the reversal must also be true. Let's try that. So how are we going to do that? So I'm going to take a copy of the A register before. Yeah, I'm just going to take a copy of the A register before. And then what I'm going to do is I'm going to look at the old A register. I'm going to end it with the negative flag bit. So that gives me just the negative flag. And then if I exclusive all that with the current with the result. So if that and that, so an exclusive OR is going to give me 0 if those bits were the same. So I want to know that they're 0. Okay. In fact, firstly, I should default to this being false, because that's definitely the default, is that it didn't overflow, and we'll try and detect the overflow. So if the two bits, the negative bits, were the same before. Oh, sorry, no, it's not the before and after, is it? It's the operand that I want. It's if the operand, the A register and the operand have the same negative bit. So that means that they were both either signed, or they were both positive, or they were both negative. Now, if that was true, if I then look at the, oh yeah, this has got to be the, yeah, no, I am right there. It's got to be the A register before. Okay, so that's right. So the A register for the before I changed it was the actual, yeah, was the operand, and the A register before. What were the negative flags in those? Then I can actually look at the negative flag in the current A register. Now, if that is not equal to either of these, really, that one, doing the same operation again there, then the negative flag, then the overflow has happened. And I can get the same effect by just doing that, can't I? Well, I'm not sure if that is utterly confusing and if that's even correct, but check operator precedence I will by just sticking some brackets around it. Okay, I wonder if that's going to pass. It does. I think that's the way to calculate that, and I could be wrong, and I'm wondering what's happening with this. I wonder if I've got some edge case that I've not thought of with this, because I've not got the carry flag involved in this yet. I'm not just adding these two values together, I'm adding these two values and the carry flag together. So I could be wrong on this, but I'd have to try and engineer a test that can make this fail, but that looks like it to me. I mean, I've done the same calculation twice there, but I'll figure what the hell at the moment. But that's looking like, you can see why this was the most complicated instruction, at least I thought of. I've done it 3 times there actually, because I've done that one as well. Yeah, I've done that one twice and that one twice. So you could clean this up, but I'm not going to do that right now. Not until I've got more tests anyway. Until I've got more that I know are actually working. So is there another test? We could do this same test except with very large signed positive numbers, couldn't we? So in this case, we could do the same test with 127. And if we add 1 to that, now the answer is 128, but that has caused a signed overflow because 128 can't be represented in a signed number. So that is going to be signed overflow is true. It doesn't cause a carry. Is it negative? I think it actually is negative, isn't it? Let's just see what this is. 127 is literally the reverse of this. We're adding 1 to it, which is, there we go. And that's going to give us a 0, carry the 1. Let's just see, carry the 1 there. Is 0, 0, 0. Yeah, it's just going to give us this. 128. There you go. Now you can see here that again the same problems happened. This was negative. Sorry, this was positive. This was positive, and we got technically a negative number out of that because this is actually also minus 100. Is that minus 128 as well? Yeah, minus 128. I did get it right. Yeah. Okay. So there is no carry. It is not negative. It did overflow, and it's not 0. So that's what we're expecting on this one. Carry is false, negative is false, overflow is true, and the 0 is false. Now I'm actually expecting this to pass because I think we wrote enough code for that previous one. Ooh, except I'm expecting it to compile. Oh, have I got the same name? Yep, I've got the same name. Signed negative, addition fails, signed positive. Had the same name, a copy and paste. Let's see what we get. That says it's failed. Negative. Oh, it is negative. Yeah, because that bit's set. Yeah, that is actually correct. That is actually a negative number because remember it's minus 128. So if that was a signed addition, you get minus 128. And the answer is it's the wrong answer. That's why the overflow flag is set. Because it's not the right value if you were doing signed. And if you're doing a signed operation, it's fine. And in that case, you don't care about these flags anyway. So it's all good. So I think this is going to pass now. Yeah. So I'm not going to say that's add with carry complete. Because we've done very few actual additions. Let's just do a really basic addition. Do a really super simple one. Because we did 0 and 0 to get 1. Add with carry can add two unsigned numbers. So these are just two general numbers with carry. Yeah, well, I won't put that because it will assume the carry. Let's put a carry on that. Let's take a value of 20. Let's add 17 and we'll get 38. And we expect the carry to be false, we expect negative to be false, we expect overflow to be false, and we expect 0 to be false. That should also pass. That's just some random value. Yeah, and let's just say add with carry can add signed and can add a positive and negative number. Let's call it that. So let's do can add 20 and we can add minus 17. And we should get the answer of 3. Oh, except we'll get the answer of 4, won't we? Is that right? Because we'll get 3 plus the carry. And again, we'll expect the carry to be false, negative to be false, overflow to be false, and 0 to be false. Should work as well. Actually, didn't. Why didn't that one work? Can add a positive and negative number. Carry flag is 1. Expected it to be false. We're not setting the carry flag correctly there. There's no carry on that. Oh, is it because minus 17 does actually produce a carry? This may have been a more complicated one than I thought. Let's just do the actual binary addition on this and let's just check it, because that's really what we're doing with these tests. We're kind of hand checking things, but we're doing it automated. So 0 and 1 is 1. That is 1. That is 1 0. Sorry. With a carry 1 there, and that's 1 0 with a carry. And there, that's 1 0 with a carry. 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 And the carry bit got set. It did get set and it doesn't overflow. And what else have we got? So that does produce a carry, and that shows you how easy it is to get that wrong. Right, so that's quite a lot of tests just for add with carry. I still don't know that that's enough. And I'm trying to think what else I would test on this. What happens if I do this one, but I have a carry as well? So in this case, I've done -128 -1, adding -1, and that produces -129, which is an overflow. So that can't happen. But what happens if I have a carry and I start with a carry on that one? So what would the actual answer be that I got on that? That's an interesting question. Is the answer -128? And here's something that I don't actually know the answer to on this one. Because we're not doing just 2 operations here, we're doing 3. Maybe we have to think about it in the way that it does it bit by bit. Let's try this. Because in effect, I think what this means is you're doing this. So this is the carry flag up here. 1, 2, 3, 4, 5, 6, 7, 8. You're taking the carry flag. You are adding -128 and you're adding it to -1. What answer are you actually going to get if you do that? If you did it as a binary addition. Let's just fill these with zeros to make it easier to start with. 1 + 1 is 1, 0 with a carry. And that gives me 1, 0 with a carry, 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 and then I finally get 1, 1. Yeah, I get 1, 1. So I get 1 with a carry. So I got a carry on that. It's definitely not negative. Did the overflow get set? It's definitely not 0. So I don't know how to represent that. There's a carried 1 there. I suppose I'll put it on down there. So what does that actually mean? In this case, my test to say that this has produced a signed overflow will say it hasn't put a signed overflow in, but has it, because we got -128. We added -1, and then we added the 1 and took us back to -128. Actually, that is the correct answer. And my overflow, it has not overflowed because it's met my criteria that these 2 are negative and we added them together and it stayed negative. So that looks like that should not expect the overflow. So this one's called ADC will set the overflow flag when signed negative addition passes due to carry. Due to initial carry flag. Wow, that's a big name for a test. That's what we're going to call it. Can I put that down there? Does that still compile? It's still too long to fit on the screen. If this works, I'm quite confident this is starting to work now. Didn't work. Negative. Oh, I do expect negative. I just did the test wrong. That is negative. Why have I put that there? That is negative, yeah. Because it's got that in it. That's a negative value. I mean, I'm saying it there. Expect -128. Right. I'm going to leave the ADC there at this one, and I think next time we'll come through and we'll just do all the other addressing modes. But I'm reasonably happy that that actually works, at least for just Absolute. I'd really like to do some tests on a proper 6502, make sure I've got this right. But there it is there, that mess. That mess is ADC. And there may be a more concise way to do it. So maybe we'll have a look at that next time. I don't know there'll be much more of a concise way to do it. It'd be nice to just set this flag once, if you could do that. And it'd be nice to not have to keep duplicating all the additions that we've done there. But from the looks of it, if I've written these tests correctly, then this actually works. So yeah, I think this is all good. So whether I've done that correctly or not, I'm not exactly sure. I think I have. It'd be nice to verify this against an actual program and see if this, I mean, actually, to be fair, I've got to implement the rest of ADC and subtract with carry before we go on anyway, if I want to run this through a program, because it can only do the absolute addressing mode at the moment, and we've got to find a way of duplicating all that without duplicating all the code. But I'm reasonably happy that I've at least got some part of ADC working there, and I think that's a pretty good suite of tests. So in the next video, definitely going to be doing the rest of the addressing modes for ADC.